The content delivery network market, valued at $23 billion in 2023, is projected to skyrocket to over $100 billion within the next decade. This rapid growth, coupled with the widespread deployment of nationwide 5G networks and the emergence of millions of small cell nodes, presents a pressing need for innovative caching solutions. With so much potential growth pending, it is only natural we examine the traditional caching algorithms to seek improvements in efficiency and cost. Traditional caching policies such as the LRU or LFU both require assumptions about the data distribution. For example, the LFU performs well with stationary distributions and the LRU performs the best with temporally local sequences. Online learning tackles this drawback by implementing machine learning methods to learn from the stream of data incrementally, optimizing the policy. This paper introduces a new metric called worst case regret to ascertain the performance of caching algorithms that rely on using an adversarial request sequence to find and minimize losses against the best non-causal static policy. The paper first analyzes the legacy algorithms using this new metric and determines their lower bounds. This lower bound measure allows us to determine how fast an algorithm can learn to cache using theoretical constraints. It then moves on to analyze the online gradient ascent algorithm using the same metric and proves that it achieves a lower regret bound. It extends this to prove this novel approach in fact has no regrets, thus it is an optimal policy. The paper also introduces a novel method for computing the projection allowing for minimal computational requirements. This approach allows the cache partitioning to be performed as a set partitioning problem rather than an exhaustive search problem. This novel approach lowers the computational requirements. Caching systems process massive amounts of low latency data every day, and performance guarantees are a must. The efficiency of the online gradient descent algorithm ensures real-world scalability. The widespread deployment of small cell networks allows for femtocaching. Small cell networks are small base stations with relatively small computational capabilities, but can be paired with enough storage to run hyper-localized caching networks. The paper also applied their method to bipart graphs to explore caching in multicache scenarios. The paper explores the setting with two types of nodes, users and caches. The goal is to determine the optimal caching configuration for the cache nodes and to satisfy the request from the user nodes while satisfying service guarantees. One difference or a unique part in the graphs is one user node is not always reachable to one cache node. As a result, they include a routing variable in the optimization goal. The system should not route a user to a cache node if it's unreachable, or the cache node does not have the file that the user requested. The paper shows that the OLO online learning optimization framework is broadly applicable to the caching setting and can be effectively used in multi-cache settings. The caching algorithm and related decision mechanism can achieve 20 to 40% higher average utility compared to legacy methods without costing too much in computational and space complexity. The paper lays the foundations for further work in this area, bringing online learning systems with caching networks. A potential future research area we foresee is the development of recommendation-based caching systems. The popular content on the web is rarely entirely random and is often directed by strong recommender systems such as on streaming and social media platforms. It might be a worthy research area to explore pairing up recommender systems with caching networks to attempt intelligent predictive caching. Thank you.